Hello everyone, I'm Quan Zhou. My advisor is Professor Li Junliu, and today I'm going to present one of the works our group has done with blue waters. It's on the western US volcanism, most intra-plate volcanism. I will explain what is intra-plate later. And this work has been published. If you are interested, you can refer to the original paper. So for the western US volcanism, this is the distribution. The red triangle here are the distribution of the western US volcanism. And the key question here is, what are the processes that form these volcanoes? And when I talk about the processes, I mean large-scale process and long-term processes. So by large scale, I mean 100 kilometers, and by long-term, I mean millions to hundreds of millions of years. And I will make this more clear later. So when we talk about the long-term large-scale Earth evolution, the most famous example is probably plate tectonics. For the western US, the western coast is actually a plate boundary between two plates. One is a Farallon plate, another one is North American plate. And as the arrow shows here, the Farallon plate moves eastward, and the North American plate moves westward. So these two plates move toward each other. And for the volcanoes here, we can divide these volcanoes into two categories based on their locations. First category is the volcano along the plate boundary, so which is the circle shows here. One example for these volcanoes is actually very close to here, 2 hours away, Crater Lake. It has a very blue water. So if you haven't visited there, you can go there after this symposium is over. And another volcanism is the intra-plate volcanism. The most famous example is Yellowstone, the Yellowstone National Park. It's 1,000 kilometers away from the plate boundary. And to explain volcanoes in geology, we have two traditional views on this. The first one is called subduction. Subduction essentially means, so as I have said, for the western US, the two plates are moving toward each other. So what happens in the vertical direction is the Farallon plate goes below the North American plate, and it goes into the mantle. And because the Farallon plate is under seawater, so it carries the water inside. And when this plate goes to the depth of 100 kilometers, like around here, the water would be squeezed out due to the pressure above it. And when the released water comes into the mantle, it could lower the melting point of the mantle above. And this melt would further generate volcanoes on the overriding plate or the North American plate. So that's how those volcanoes along the plate boundary were formed. And another traditional view is called mantle plume. So for mantle plume, the plume is a hot mantle material rising from the bottom of the mantle. And the bottom of the mantle is 2,800 kilometers deep, contrasting to the 100 kilometer deep for the previous subduction process. However, for the Yellowstone volcanism, because it's 1,000 kilometers away from the plate boundary, and we cannot use the subduction process to explain it. So most people refer to the mantle plume to explain the volcanism there. If you go to the Yellowstone National Park and you read those introduction on Yellowstone, they will tell you it's a mantle plume. But from present-day observation, we think there is, this explanation is very problematic. And to understand how the mantle evolves to form the Yellowstone volcanism, we must refer to the structure of the mantle below the surface. So how do we know the structure? We use a technology called earth tomography. So when an earthquake happens, it would generate elastic waves traveling in the mantle, and we could record the signals from these elastic waves and refer the structure of the earth interior. It's kind of like medical tomography, just it's from elastic waves. And for the western US, or for the whole United States, the tomography we see here is something like this. And the traditional is the blue means something strong and cold, And a reddish stuff means something cold and hot and weak. For the United States, the key thing here is we have both hot anomaly and a cold anomaly in a shallow mantle and in a deep mantle. So I will show how the Earth has evolved into this structure later. And to study how the mantle evolves over time, we use Earth mantle simulation. In a long-term sense, from millions to hundreds of millions of years, we treat the mantle as a viscous fluid, and we solve Navier-Stokes equation to solve this problem. And we assume the mantle is incompressible, which is reasonable for the mantle case. And so to do simulation of mantle, we normally use data assimilation mantle convection. We use data assimilation because we want to simulate real Earth. By real Earth, we mean how the real Earth evolves over time, not some idealized 2D simulation. And data assimilation essentially means we incorporate some data into the model to guide the model to evolve. And in mantle convection simulation, the data we can use includes plate motion and seafloor edge. Plate motion and seafloor edge are from the magnetic data in the seafloor, from the seafloor, and they are very accurate. And now we can refer back to 150 million years ago or 250 million years ago for plate reconstruction. Another type of data we can use is tomography, the current 3D image of our Earth. And this is the 3D tomography for the Western US. And again, this reddish part represents the traditional view of plume. This blue to yellowish part means the cold downgoing plate. And as you can see, the downgoing plate blocks the plume to reach the surface. So for data simulation in our field, we have different data simulation methods. And first one is a forward or sequential data simulation. For this method, we solve the governing equation forward in time, and we use the plate motion as the velocity boundary condition, and we update the oceanic lithosphere, the upper layer of the Earth, the temperature of it from seafloor edge by some physical laws, thermal diffusion law. And the good thing about the forward or sequential data simulation is it could simulate how downgoing plate evolves over time very well, including a nonlinear behavior like the broken slab, broken plate. And however, the problem for forward or sequential data simulation is it does not have a proper initial condition, since we are solving a time-dependent governing equations. So to solve this, people first propose simple backward inverse model. For this model, we solve the governing equation backward in time, and we neglect the thermal diffusion or use the normal thermal diffusion. However, as we know, thermal diffusion is not inversible in time. So this is also problematic, especially it cannot properly resolve the nonlinear behavior of mantle. And another method is called adjoint or variational data assimilation. This method tries to solve the initial condition problem, but it's better than a simple backward inverse. In philosophy, the process for this method is we have a first guess on initial condition, and we run the governing equation forward in time to get a prediction on present day. And normally, the prediction has a mismatch with the observed tomography. Then we calculate the mismatch between the observation and the prediction, and we transport this mismatch backward to the initial time and the correct initial condition. And then we run this iteration forward and backward for several times until we have a good prediction on present day observation. But we have applied these three methods for the United States, and they cannot provide a very good solution to answer the question of how Yellowstone was formed. So to solve this problem, we further propose a hybrid data assimilation method. It's essentially a combination of forward data assimilation and adjoint data assimilation. So with the forward data assimilation, it could have a good simulation of the downgoing plate. With adjoint data assimilation, it could restore the initial condition. And with this, as I will show later, this is the best method we can do to study the evolution of the western US mantle. And then, so why we use blue waters? So CitcomS is the open source code we use on blue water for our simulation. It has a very good scalability, up to 10,000 CPUs on blue waters. And for some other ongoing project, we are doing global mantle simulation. We will use this much CPUs. So this is very good for us. Also, Blue Waters is compatible with the open source software we are using. For example, CitcomS, DirectS, and FStrike. So that's why we use Blue Water. And one of my colleagues back in China, he does not have access to supercomputers, and he runs similar scale model as mine. For his model, he needs to run for each model maybe 1 week to 1 month, and I run thousands of models for this study. So if I didn't have access to Blue Waters, this work would be my only work for my whole life. And so now I'm going to the results of our study. The first row here is the observation of the tomography in the western US. The second row here is the modeled results. As you can see, in large spatial scale, they could match each other pretty well, but in small details, they cannot match. But that's not the key point here. And next, I'm going to travel backward in time to see how the mantle below western US evolves over time. So first, this cross-section, by cross-section, I mean the vertical direction of a slice along the vertical direction of the Earth. And this cross-section is along the profile of A, B, C, D here. And to make it more intuitive, this location is the western coast, the plate boundary. This whole area is the continent. And this small tiny area is for the oceanic plate, okay? So, and this reddish, this hot anomaly at 600 kilometers is the restored plume. So if I play this time sequence forward in time, this 20 million years. MA means millions years ago. That's what it means. If I place time sequence forward in time, so as we can see, at 18 million years ago, some hot anomaly from shallow mantle, from shallow mantle, like from around 200 kilometers, came below the oceanic plate and tried to break this plate into the continent. And so at 14 million years ago, the hot anomaly almost broke the slab and moved into the continent, which is here. And if you pay attention to the plume here, its overall evolution is the main body of it. The main body of it is moved downward in time, not upward in time. So this is the present day prediction for this profile. Again, it matches the observation. So from this, we can see the plume here moved downward instead of upward as the traditional point of view. So we think the plume cannot contribute much to the Yellowstone heat source. And now here is a 3D view of this. All the 3D illustration here is for the hot anomaly in the mantle, and only this blue curve is the western coast. If I play this elevation, you will see the shallow hot mantle in the continent all came from the below the oceanic plate, not from the plume. So this is how it goes. And we further validate our model with, sorry, I don't know why the sequence always goes. We further, we further validate our prediction with the observed eruption of volcanism. The black dots here are the reconstructed volcanism backward in time, and as this map is for 40 kilometers deep, so it's very shallow in the mantle. And as you can see, the hot mantle evolution could roughly follow the evolved eruption of volcanism observations. So we think our model could predict the intra-plate volcanism for the past 16 million years in the western US. And to further understand the dynamics to drive the evolution, we try to remove the ancient Farallon slab here, which is very deep, between 600 kilometers to 2,000 kilometers. If we remove this, the hot anomaly is the yellowish part here is restricted near to the plate boundary instead of going to the Yellowstone. Yellowstone is here. So the story here is the sinking of the Farallon slab drives the whole mantle towards it, including the hot anomaly, and the main body of the plume was also driven downward by the Farallon slab. So this comes to our conclusion. The sinking ancient Farallon slab drives the hot anomaly below the oceanic lithosphere to intrude into the western U.S. And the propagation of the oceanic hot anomaly below the western U.S. could predict the intra-plate volcanism. That's it. Thank you.